In order to understand how spectroscopy is used for structure determination, we're going to first have to review some of the basic features of light and matter. Electromagnetic radiation, or light, exhibits both wave-like properties and particle-like properties. Consequently, electromagnetic radiation can be viewed as either a wave or as a particle. You might remember this when you studied quantum mechanics in general chemistry. When viewed as a wave, electromagnetic radiation consists of perpendicular, oscillating electric and magnetic fields, as is shown right here. The wavelength, for which we use the symbol lambda, describes the distance between adjacent peaks of an oscillating field. The wavelength describes the distance between adjacent peaks of an oscillating field, while the frequency describes the number of wavelengths that pass a particular point in space per unit time. For frequency, we use the units reciprocal seconds or hertz, which mean the same thing. A long wavelength corresponds to a small frequency, because if the wave is big, we're going to have less waves that pass per unit time, and a short wavelength corresponds to a large frequency. So if we have a short wavelength, we're going to have more wavelengths pass per unit time. This inverse relationship is summarized in the following equation, that frequency is equal to the speed of light divided by our wavelength, which shows how frequency and wavelength are inversely proportional. It's also handy to remember the speed of light, which is about 3 × 10⁸ meters per second. When viewed as a particle, electromagnetic radiation, or light, consists of packets of energy called photons. The energy of each photon is directly proportional to its frequency, and that's shown in this equation right here. Energy is equal to h times the frequency, where h is Planck's constant, which is 6.626 times 10 to the negative 34 joules times seconds. So you can see here that if the units for Planck's constant are joules times seconds, and we multiply that by our frequency, which is reciprocal seconds, we get the seconds canceling out, and we get that we're going to get the energy in the number of joules, or the amount of joules. Before we move on, I just want to point out also that wavelength is inversely proportional to energy. And the way that we determine that is that if energy is equal to h times nu, the equation we have above, and we know that if frequency, nu, is equal to the speed of light over wavelength, we can plug this equation in here, and we can get that energy is equal to h times c over lambda. And this reveals to us how energy and wavelength are inversely proportional. And the take-home message is that short wavelengths will correspond to high energy, and long wavelengths will correspond to low energy. The range of all possible frequencies is known as the electromagnetic spectrum, which is shown here. The electromagnetic spectrum is arbitrarily divided into several regions by wavelength. You can see that the visible portion of the electromagnetic spectrum corresponds to a very narrow range of wavelengths. Different regions of the electromagnetic spectrum are used to probe different aspects of molecular structure. In this section, we will learn about the information obtained when infrared, or IR, radiation interacts with a compound. And what makes infrared spectroscopy so powerful is that the information that we can obtain is information about functional groups present in the compound. Based on a compound's infrared spectrum, we can determine whether the compound might be a carboxylic acid, or an ester, or a ketone, or a primary amine, or a secondary amine, or an aldehyde, so on and so forth. So again, the information that we get from infrared spectroscopy is about the functional groups present in a compound. Later on in this course, we'll take a look at NMR, which is nuclear magnetic resonance spectroscopy. And the information that we get in NMR is the specific arrangement of all carbon and hydrogen atoms in the compound. And basically what that means is that we're able to determine the connectivity of the carbons and hydrogens in the compound. Matter, like electromagnetic radiation, also exhibits both wave-like properties and particle-like properties. Earlier on, we saw that quantum mechanics describes the wave-like properties of matter. According to the principles of quantum mechanics, the energy of a molecule is quantized. To understand what this means, we're going to compare the rotation of a molecule with the rotation of an automobile tire connected directly to a motor. When the motor is turned on, the tire begins to rotate, and a measuring device like a speedometer is used to determine the rate of rotation. Our ability to control the rate of rotation appears to be limited only by the precision of the motor and the sensitivity of the measuring device. What that means is, let's say we wanted to get this tire to spin at, let's say, 40 kilometers per hour. Well, there's no reason why we couldn't get it to spin exactly at 40 kilometers an hour. What if we wanted it to spin at 40.01 kilometers per hour? Would that be conceivable? Absolutely, we could do that, right? We would just press the accelerator a little bit more, we'd get it exactly at 40.1 kilometers per hour. What if we wanted it to spin at 40.12 kilometers per hour? Could we do that? Sure. We'd have to be very careful, but we can do it. What if we wanted it to spin at 40.1238, 1 kilometers per hour? Could we do that? Yes, there's nothing preventing us from doing so. In contrast, molecules behave very differently. The rotation of a molecule is going to be restricted to specific energy levels. And that concept is shown to us right here. So we have energy and we have different vibrational states. And the point is this, is that molecules exhibit quantum behavior. That means they can't vibrate at any energy level. They can only vibrate at specific energy levels. The rotation of a molecule appears to be restricted to these very specific energy levels that are shown here. That means that it can't vibrate anywhere in between. These are not allowed. It can only vibrate at these specific energy levels. These other rotation states are simply not allowed by the laws of physics. And again, we say that the rotational energy of the molecule is quantized. Molecules can store energy in a variety of ways. They rotate in space, their bonds can vibrate like springs, their electrons can occupy a number of possible molecular orbitals, and so on. Each of these forms of energy is quantized. For example, a bond in a molecule can only vibrate at these specific energy levels. The horizontal lines in the diagram represent allowed vibrational energy levels for a particular bond. The bond is restricted to these specific energy levels that are shown here. This one, so on and so forth, like that. It's restricted to those energy levels and cannot vibrate with an energy that is in between the allowed levels. The difference in energy, or the delta E, between allowed energy levels is determined by the nature of the bond. What we will see in a little bit is that delta E is related to things like bond strength, or the mass of atoms in the bond. So mass of atoms in the bond. Because vibrational energy levels for particular bonds are separated from each other by specific energy gaps, or delta E's, if a photon of light possesses exactly this amount of energy, so the correct delta E, or the exact amount of energy in between vibrational energy levels, the bond can absorb the photon to promote a vibrational excitation. The energy of the photon is temporarily stored as vibrational energy until it's released back into the environment, usually in the form of heat. Each form of spectroscopy uses a different region of the electromagnetic spectrum and involves a different kind of excitation. Again, in this chapter, we're going to focus on the interaction between molecules and infrared radiation, which promotes vibrational excitations of the bonds in a molecule.